So, hello everyone. This is once again Paul, Cellular Locality. And so in the last video, we expanded on the idea of the binomial theorem and the whole idea of using numbers that are from Pascal's triangle as coefficients within the binomial theorem. So we used that technique to solve an expression which was 2x plus 3 all squared. So we solved it using the binomial theorem, and then we got the same answer that we got when we solved that same expression using expanding and simplifying. Therefore, we then proved that the binomial theorem actually works. So in this video, we'll be continuing more on the topic of the binomial theorem and on the idea of using the same coefficients from Pascal's triangle, or the same numbers from Pascal's triangle as coefficients for the binomial theorem. So let's first solve the expression a plus b all cubed. So when we solve this expression, what we will get is we'll get a to the third plus a squared b plus a b squared plus b cubed. And then from there, since a is equal to 2x, wherever there's a, we put 2x. And since b is equal to 3, wherever there's b, we put 3. So therefore, since it was a squared, we put 2x to the third. Sorry, I meant since it is a to the third, we put 2x to the third plus 2x squared times 3 plus 2x times 3 squared plus 3 cubed. And then from there we get our answer of 8x to the third plus 4x squared times 3 plus 2x times 9, which is, we got the 9 by squaring the 3, and then plus 27, which is 3 cubed. And then from there we get 8x to the third plus 12x squared plus 18x. So we got the 18x by multiplying 9 by 2x, and then plus 27 yet again. And then from there what we will do is that we will take the numbers that we got here, and then from there we will multiply them by the coefficients that are the numbers within Pascal's triangle. So since here we're dealing with an expression that is cubed, this means that we're dealing with an expression in row 3, and the numbers in row 3 are in this order: 1, 3, 3, 1. So from there we take these numbers and then we put them in front of, we put these numbers, which are the numbers in Pascal's triangle. We take them and we put them as coefficients to the numbers that we got when we were solving for this expression in this part. And so from there we say such that 1 multiplied by 8x to the third, 3 multiplied by 12x squared plus 3 multiplied by 18x plus 1 multiplied by 27. And so we get 8x to the third, 36x squared plus 54x plus 27. Now, yet again, this is the same answer that we got when we were simplifying the same expression using expanding and simplifying. So let us then solve another expression, which is pretty much the same expression, 2x plus 3, using the binomial theorem, except now it's all to the fourth. So this is going to be such that we'll first get a to the fourth plus a to the third b plus a squared b squared plus ab to the third plus b to the fourth. And so from there we put 2x wherever there's a, and then we will put 3 wherever there's b. So we do this process, and then after plugging in all these numbers, which is we plug in 2x where there's a, and then 3 where there's b, we multiply them yet again by the numbers which are in the fourth row of Pascal's triangle, and multiply them by all these numbers as their coefficients. So from there, we will then get an answer of 16x to the fourth plus 96x to the third plus 216x squared plus 216x plus 81. Now this is the same solution we got when we're simplifying the same expression using expanding and simplifying. So all of these ideas, generally, they are there to just prove that the whole idea of the binomial theorem with regards to Pascal's triangle as well actually works. So from there, let us then talk more about the binomial theorem in general. So as I stated earlier on, that I like to think of the binomial theorem as this statement: a plus b is to the power n. So this is going to be such that it will equal to a is to the power n plus all these terms which are in between up until you get to the last term, which is going to be b is to the power n. So what you do this whole time is that in this repetitive sequence and pattern of terms, what you do is that you drop a and then you raise b. So for an example, if we have 3x minus 4 all to the third, such that wherever there's a, we substitute with 3x, and then wherever there's b, we substitute with negative 4. So since the bracket is powered by 3, we will use again a plus b all to the third. So a plus b all to the third, it will equal to a to the third plus a squared b plus a b squared plus b to the third. And so from there, wherever there's a, as we said, we substitute with 3x. Wherever there's b, we substitute with negative 4. So this is going to be such that it will be 3x to the third plus 3x squared times negative 4 plus 3x times negative 4 squared plus negative 4 to the third. So this is going to be such that it will be equal to 27x squared plus negative 36x squared plus 48x plus negative 64. And so from there, we get an answer of 27x squared minus 36x squared. Sorry, I meant 27x to the third minus 36x squared plus 48x minus 64. So from there, since we get all these numbers over here, now we know that we're dealing with numbers which are in the third row of Pascal's triangle. So we put coefficients. We put the coefficients which are the numbers in Pascal's triangle. We put them in front of the numbers that we got when we're simplifying this expression. So it will be such that 1 multiplied by 27x to the third minus 3 multiplied by 36x squared plus 3 multiplied by 48x minus 1 multiplied by 64. And so from there, you will get 27x to the third minus 108x squared plus 144 minus 64. So this is the same answer, yet again, that we got when we're simplifying the same expression, which is 3x minus 4, using expanding and simplifying. And so from there, we will expand more in the next video on this whole topic of the binomial theorem yet again.